TomoPyUI is built on TomoPI, which is an API, a Python API for reconstruction and alignment of tomography data. And there's all sorts of different functions that TomoPI has built in, but you have to sort of write a script and change different parameters. And if you don't know what you're doing, it's kind of difficult to like choose all of those parameters. So what I built is something that people can just go through quickly and visualize their data along this processing pipeline. So this is in Jupyter Lab, which is within like the Jupyter sort of ecosystem. The install process for this is relatively straightforward, and I have the whole thing on the website. But basically, you just open up Jupyter Lab and run this after you've installed it. So we'll just like run that first cell. Might take like 1 second for it to pop up again. But then you'll see this, this dashboard. And the various different things throughout the dashboard are about importing data, pre-processing data, finding the center of rotation of your tomography, alignment and reconstruction, and then finally you can like look through your data in this Data Explorer tab. So I have a couple of folders here. These are just like any typical folder that you might have for your data. And so what you do once you get your data off the beamline, you can do this like right as you're taking data, so you can kind of make the next steps in your experiment if you wanted to. You just pop that the path with your raw data into this import and normalize raw data tab. And then it will detect if you've collected this data at different energies. It'll detect all of the energies within that folder. And so this one is a higher energy, it's above the cobalt edge. So it's detected that it's at 8,000 EV. And then it'll show you metadata and information about your sample. So these are just like the parameters you're choosing for within sorry, is it XM Flex? Yes, XM Flex for SSRL data. You chose these different layers within XM Flex. You chose the different number of reference exposures and how many references you're taking across the whole data set, blah, blah, blah. So once you do that, you just click this upload button. It'll upload all of the XRMs in that folder into memory. And then it will normalize the data. So you divide by the references and you take the minus log of that. And then so it'll show up soon inside of this viewer here after it does some pre-processing. So you can sort of immediately visualize your data. So it does this step called downsampling, which means that you're taking your data, which is 1024 by 1024 or double that, and it samples it downwards so that you're only looking in this viewer at a lower resolution. You can change that here. So right now it's at a quarter of that data. So 256 by 256, and that makes this a little faster to view. But if you wanted to really see what the higher resolution of your data is, then you can pop this in to 1, and then you can see that it is a higher resolution there. So it might, you can see that it's kind of like slowing down because it's a really large data set. So that's why you should, if you wanted to, you can downsample this data. Now, this is not changing your actual data. It's only changing the view of the data. So you're not really changing any data when you're downsampling in this viewer. Okay, so the next step is to do some pre-processing to your data. If you wanted to add any filters to your data before you did any further steps, then you could come to this tab, Prep. And so I'll click this button. It says click to use raw or normalized data from the import tab. And then you can look at the projections here again. So this is that raw data that raw and normalized data that we just imported. And then for alignment, it can be better to use a filtered data set. Some of the information, some of like the high frequency information, you know, in this noisy part of the data can get in the way of the alignment, at least I've found. So we can add some filters. Right now, there's only 2 available, but this could be expanded later on. So to do this, what we do is we click on this button, and I'll try to make this more obvious. But we'll click this button, and that kind of brings this over to another viewer here called Altered Projections. And we're going to take this data here, and we're going to change it with these methods. And it's going to change the data set and save an altered data set. So again, we're not changing the original data set. We're just changing these altered projections here. Okay, so say I want to do a median filter on my data. And just to give you an idea of what that's going to look like, we click this button, it goes into the methods thing here. And if we just want to preview what that's going to look like, and I'm going to make sure that this sampling is back at 1. So we just, yeah, so if we just want to preview what that's going to look like with the size, a median filter size 11, we can click this run button, and it'll show you how that's changed the data. And so you can see kind of before and after that what that kind of does to the data. Then I'm going to apply this to the full data set. And so I'll click this button. It turns on saving. I'm going to unclick the preview button. So this is, once I apply these filters here, any filters that I want, I can add more if I wanted to. So I'm going to, you know, remove these guys. So I just want to do a median filter. And then I'm going to click run, and it's going to do the median filter across my entire data set and save it. So it's going to take a second. I'm eventually going to add an option for a GPU median filter. Right now, this is just a CPU-based median filter. And so that will speed up significantly the process. But so now what you have in this altered projections here is your entire data set that has been median filtered. Eventually, I'm going to add a button that says, okay, now that I've done that, I'm going to use this for the rest of the processing pipeline. But for right now, we're going to come down to this other tab called Import Pre-Normalized Data. So now that we've normalized the data, and we've done some pre-processing steps, I'm going to, again, go into this other folder here, which is, this is the folder that I've now saved this particular energy in. So this is my raw data folder. And then once it did the normalization process, it saved it inside of this, this subfolder here. Along the way, it's saving all of this metadata about your data. So this is, and I'm going to clean this up eventually, but this is the first part of the process. So this is the raw data, this raw metadata. Once it's normalized it, there's some other information that you can get. These are basically the same right now, but eventually I want to put in something where I can, you can see every part of the process that you've done, basically, when you throw in a folder here. So anyway, we're going to go into this prep folder, which is now, you can see that it's time-stamped with when we did that median filtering. And this is just another folder with new normalized projections. I click this and load it in. Again, it's going to write some downsampled data so that you can easily view it faster in the future. This takes a second to do that. Okay, so now this is a median filter data set. The next step is to find the center of rotation. So again, these reset. So I'm going to now click this use pre-normalized data. And it'll throw that data inside of this center finding part. Now, the center of rotation typically is rough from like, you can get a good rough estimate from the center pixel. So if you click this button, it'll load in the center pixel as your center of rotation. But in reality, that's not usually the center of rotation. It's some offset of that. So you can kind of like scroll through your data again to see if that's a relatively good estimate of your center of rotation. It's pretty good for this particular data set, but in some cases it can be over here or over here. So you have to check that out. And so one way to check this is by doing a reconstruction on a given slice of your data. So this automatically uses the center slice. So it's going to reconstruct data at this point along the data set. So what these different options are this is the guess for the center. So this is the center point right here. The slice again is the slice that you're going to use through the Y direction. So if I use slice, I don't know, like 10, you wouldn't get any useful information from what we're about to do, but any place where you have like a particle or something in your data you want to look for. Okay, so this is the slice, and then this is the number of iterations for this particular algorithm that we're going to be using. We're just going to stick to GridRect because it's fast, but you can choose these various different algorithms if you wanted to. So here now, I'm going to look for some pixel range around this value. So this is at 512. I'm going to search like 200 pixels in either direction. So I'm going to go over here to over here, and it's going to reconstruct using this center of rotation along that pathway. So the step size, if you decrease the step size, this is 0.5, it's kind of small. So we'll just do 20 pixels as the step size between those two ranges. And then you click this button, it says it'll do this reconstruction along those centers. So then once you plug that in, you can see that the reconstruction of this slice changes significantly as we change the center of rotation of the tomography. So what you want to kind of do for reconstruction is find a good one. I don't know, like it looks better here. There are also some automatic center finding algorithms, but it can vary. Their efficacy can kind of vary based on how noisy your data set is or not, and how aligned your data is. So for right now, that's pretty good. But if I wanted to go in closer to getting a sort of like make the center of rotation search finer grained, then we can search 50 and 1. The step size is going to be 1. So you'll see the result of that. Once I plug this in, it's now automatically updated the guess. And so it's now searching 50 around this 532 on either side. Okay, so let's take a second. And then you can see that this this search is a smaller range. And we're kind of just trying to hone in on a relatively good one. So that's pretty good. For alignment, it's not it is a critical aspect of it, but it's not the most, because based on the center of rotation you choose, it can, the whole data set will shift based on the center of rotation that you choose. That's a little bit too much information, but here, we can just say 521 is fine for the alignment part of the process. Okay, so now we come to align. This is the alignment tab, and again, we've filtered the data prior to this step. So the alignment, what it does is you're taking some part of your data, you're reconstructing it, then based on this reconstruction, you're then reprojecting the reconstructed view. And so you're reprojecting it and trying to match that reprojection up with your original data set here. So this process can be really slow if you use your full data set. And so the idea for this tab is to kind of reduce the amount of data that you have that you're throwing into this algorithm, so it's much faster. Okay, so here I'm going to, again, this same kind of button here, I'm going to click to copy my data over to the altered projections. And then I'll select a region of interest in my data that I want to align to. There can also be some problems. So for example, if you look at my data, some stuff is coming way in and out of the field of view. So like this part of the data is way out of there, and then it's coming into the frame, and then it's going back out. So that can also cause problems with this alignment algorithm. And if you had just taken your data and thrown it into TomoPy without knowing where you're actually aligning to, you might come up with a really poor result for your data. But here, what you can do is you can select a region within your data set. So I've now selected this part of my data that I want to use to align to. And so that's pretty much all of that stuff is pretty much in my data set the whole time. There's some of it that's going out, but it's not as bad as this section. So then I'll click this button, which is it gets this range, and it throws it into these altered projections. So what you can do here is you can kind of see, if you click this link button, you can see how these are changing. This is updating this slider, and so you can kind of look at these things as sort of as one. So this is what we're going to be aligning to. This is just the raw things that you've loaded into the app. Now this other section here, this other button, which is an ROI for the altered projections. Again, part of this algorithm is it compares, and I'll show you this when I actually run the algorithm, but it compares this data set to a reprojected data set after you've reconstructed it. And the region in which you compare the data set also matters. So what we're going to do here is set a region to compare to. So if I just had, if I wanted just to compare this part of my data set to the reprojected images, that's what it would do. Okay, so I'm just going to make this like relatively, large. But you can also zoom in on where you're actually comparing the data. Okay, so once that's finished, you can click this button here. I think I'm going to also change this in the future, but for right now, I have a button here that says click to use the altered projections. So click here to use these guys for the alignment. Then you come down to a part of the, this is the methods that you can use, the reconstruction algorithms that you can use. Typically, CERT is good for this alignment. but this is something that is nice. You can kind of play around with different algorithms to see which one works better for your data. It may be that any of these other ones may work better for you. It just depends on the data set. But these are all, yes.
I have a quick question. How does that contrast to art? Because I've been using art as the algorithm for all of my stuff, but I don't really have a good handle on how that differs from, I didn't know there were so many.
There are a ton of them, and I don't know anything about them. So like these are all available in TomoPy. They've done the development for it. I'm meeting with the people that have developed it later today. For reconstruction of a full data set, what I've found is that this MLEM is actually really good for, at least for, some of the data that I've reconstructed. It seems to be better than some of these other methods like ART and SERT. Again, I don't really know the details about these algorithms. So
but actually, I don't know. I don't know whichever. You can also, I mean, there's publications on every single one of these algorithms, and a lot of them compare and contrast each other as well. Sometimes with real data, oftentimes with fake data. But they will tell you sort of, this one's really good for, heavy metal artifacts or things like that. But there's an infinite number of them.
Yeah, there's just so many. But the nice thing is that if you want, you can like click all of these and run all of them through. Okay. And so for alignment, you really kind of only want to choose one at a time. I'll show you why in a second. But if you clicked, you click all of these, and then you could run them all through the reconstruction, and then you could come up with, you're going to come up with like 6 folders with, these various different algorithms that you've used. Now, these ones up here are just the regular TomoPy ones, and they don't have GPU capability, but these Astra toolboxes, they have all these algorithms with CUDA, which significantly improves the speed of reconstruction and this alignment scheme. Okay, so after you've chosen whatever algorithm you want to use, then you come to this part, which is about saving. So this is the tomography. So you're going to take this data set, you're going to do this alignment. It's going to come up with some amount of shift for each projection. So you can see how jittery this data is. It jumps around a lot, but you want to find the distance between, you want to find something where it's not going to jitter, and so you have to shift this just like the manual alignment in the in TXM Wizard. So it's going to come up with some values to how far to shift each projection, right? You can save the tomography of that shifted afterwards before, so you can save the raw data, you can save the final reconstruction that it did, which is not really important, but you might want to have it. And then you can save it in either TIFF or NPY. So this is a NumPy binary, which just makes it faster to load in your samples into NumPy in the future. Yeah, so, okay, so then these are the options for aligning the data. So this is the number of total iterations it's going to go through. So what we'll do for now is just say 15. I don't know. Yeah, 15 is fine. And then again, this center of rotation you've already found in that previous tab. Upsample factor, this part of this algorithm is you turn your data into, you Fourier transform your 2D data, and then it tries to locate the peaks in the Fourier transform, and it tries to match those up. And this upsample factor basically gives you like sub-pixel precision, I think, in Fourier space. So this transforms it so that you're now upsampling your data, and it gives you sub-pixel accuracy in this comparison. For this is the number of batches we're going to send to the GPU at one time. Again, eventually I'm going to make this so that people don't have to put this in. But depending on how good your graphics card is, you might have to go higher with this number. So, you know, if my graphics, the graphics card on this computer is really good, so we can send a lot of information to the GPU at one time. But if you only have like 1 GB of data on your GPU, you might have to increase this to something like 40 or something. And this is something that I want to just get rid of so that nobody has to worry about it. But 20 seems to be fine for me, but you might have to play around with that if you have not a whole lot of memory on your graphics card.
Hey, Stan, can I ask you a question real quick?
Yeah, go ahead.
For the save options, if it saves a TIFF, what is that TIFF of? Is it a stack of TIFFs or is it a TIFF of the?
It's a TIFF image. It's just one image. So it'll save, okay, so if you click, say for example, you clicked all 3 of these and you click TIFF, it would save all 3 of these as TIFF. And if you click both of them, it would save all as TIFF and NPY.
But I think she's asking
okay.
sort of, what do you, for Tomo after, is it a single projection image? Is it a single
No, yeah, yeah, so that's a good question. And I think I'm gonna, again, change some of the names here to make it more clear. But this is just the aligned tomography, all of the projection images in one TIFF image. So
it's a stack of, yeah, okay. So it's a TIFF image that's a stack of TIFFs.
Yes, yep, and then again, this option is good if you just want to. So, but all of this is fine. You can save all of this information if you wanted to, but I'll show you why you don't really have to necessarily coming up in a couple of slides. So, okay, so I'm just gonna run this. Have I gone through all of it? Okay, so padding is important here. So we're gonna add padding to the sides of this data. So it's gonna come over here. We're gonna add some over here and above. So in X and in X and in Y. Okay, so we want to give it a good breadth on X, and in Y it's not too bad for this sample, and typically it isn't, because you can see like it's not jumping around too much in Y, but it is in X a pretty significant amount. This next part here is critical that you do when you're aligning your data. So we want to downsample our data, and right now, if I did this at the full data set, it would take a really long time. In addition, this algorithm in particular wouldn't work because it requires like not only the tomography to go to the data, the GPU, but the tomography plus all of these like intermediate parts of this algorithm have to be stored on the GPU. So this algorithm is cert3D. It takes the full data set. So it's fast, but it requires a lot of GPU memory. So we're going to downsample the data so that it's less data that the GPU has to handle, and less calculations.
Sorry, are you downsampling by pixel? Is that what you mean by downsampling? Not by angle?
Not by angle. Just all of the projections are still there, but all of the X and Y of your data. So this will basically just look more blurry. Each of these images will look more blurry because they are just lower resolution.
Blurry or pixelated?
Yeah, well, more pixelated. I think it's some kind of bicubic interpolation that the downsampling does.
Okay.
Yeah. So in effect, it will be more blurry. Okay, so There's another option for pre-alignment iterations. If you wanted to do the reconstruction a ton of times before you started aligning, and you'll see why that may be important in a second. I'm just going to start running it because it'll take a little bit of time. Let me just make sure I have everything set up. Okay, so what you'll see is that this is just a sample. So this is the projection number 50. So if we go up here, it's the 50th projection. It has started reconstructing the data and then reprojecting it. And these are the two images that it's comparing between. These are the shifts in X and the shifts in Y across the full data set. So this is the first projection, and this is the last projection that you've taken with your raw data. This is some convergence criteria that the people at that developed TomoPI have come up with. So you can read about that in their paper on this particular algorithm, and I can send that paper out later on. So it's done all of that. It's now gone through these iterations of this alignment algorithm. It's compared these two images. It's come up with some various shifting for your data set. You can see how that's working across the full data set. You can see that the X pixels are really, the jumps in X are really large and Y is not so much. Once that's finished, you can look at how this has changed your data. So you can see that, you can see by the borders here. Maybe I can make it more clear by changing this scheme here. You can see that on the borders of your data, it's like significantly, it's jumping around on the borders, but your data is much more stable, right? So that's the whole idea with alignment. You just want to get rid of these jumps, and it does that by shifting the original data set and padding it. So now we have.
Do you have negative values in there? Why do you have something that's darker than 0?
Darker than 0?
Yeah, you've padded with zeros, right? But the corners of the original image are darker.
Yeah, so we can, that's something else that I'm going to add, is getting rid of these dark, anything less than 0 in the log.
Okay.
It can affect this particular algorithm, MLEM. So that's something that I'm going to add in the future for in this prep tab here.
Mm-hmm. Mm-hmm. Okay,
so we've done that. We didn't, you saw that we didn't save anything, and I want to now shift my original data set, because remember we did this for the median filtered data set. So I'm going to come back and load in my original data set that I took. So if we go here, you can see that this is the prepped data. So what we are looking for here is this guy. So this is my original data set that hasn't been shifted. I'm going to load that in again. And then I'm going to come up to prep again, and I'm going to remove that median filter. I'm going to now upload shifts from previous alignments. So let's go here again. Here is the prep. Here's the alignment that I just did. And all that was saved inside of here, you can see that it saves the method. If I did 5 different methods, 5 different things would show up in here. And then I'm just going to click this, and it loads in all of the shifts in X and Y's. Then I'm going to load that into this methods thing, just like I did for the median filter, and I'm going to shift my data. So again, you have to pull this over from the original data set. Let me first, I didn't do this, to use the pre-normalized data. Load this in. You can see that this is my kind of fuzzy original data without the median filter on it. And I'm going to shift this data set and save it. So it's going to go through this shifting process. You can see that that is now shifted. So this is the original data now shifted. Okay, finally, I'm going to come to the Reconstruction tab, and what you'll see here is a bunch of the same info that we had previously, but because, again, we still choose all of these different algorithms for the reconstruction. So I can choose all of these different things, let it sit, run, and it'll fill up a folder filled with, these different algorithms for reconstruction. I can do the same thing here too, though. I can pull my data over and choose one part of the data set to reconstruct, because again, when you if you have like a part of your data that you don't care about, you don't want to like spend time doing the reconstruction on that part of the data. So I can just click this, it'll load in this section of it, and then this can be used for the actual reconstruction. And finally, then you just go through the same process. It has less options here because you don't have the upsampling part of it. You don't have these different phase correlation section of the reconstruction. You're just loading this into these algorithms here. Again, you can try all of them. Okay, so I'm not going to run that because it's just going to make the program hang, but you get the idea. If you have any questions on this tab, you can let me know. But I do want to show you another feature that I've recently added.
Really quick, so for this, do
yeah.
you need to check any of those save boxes?
Yeah, so for this, you do need to check those save boxes. And so the save boxes you'll check are just the recon. If you can check. Typically what I do, and I think I'm going to make this default, is just clicking this on so that it's automatically saving the reconstruction and saving it as TIFF too, because now once you have this, you want to then load this into Dragonfly to look at it really quickly. So that's what I'll make it as a default. Yeah, I was thinking about that too, because I always click recon and TIFF because I just want to pop that into Dragonfly to look at the final reconstruction.
It's a little confusing that you can actually click recon and not define what the file type is. Like, what happens if you just click recon and no TIFF or NumPy?
Yeah, so then it does default, I think, and I have to look back at that, but I think it defaults to saving TIFF.
Okay.
So if you just click, yeah, I agree that that's confusing. It's something that is yeah, there's a lot of features trying to put in, but I think it will just default if you click just the recon. And I'm just going to make this as a default because what's the point of even doing a reconstruction if you're not saving the data, right? But what's nice though is within the Align tab, you don't have to save these intermediates because that just takes up data. It takes time to write the data sets, and then you can just shift based on uploading these shifts from the previous alignments part. Do you have something?
Yeah, I had a question. Have you explored whether or not right now you're centering, you're finding the center of rotation, then you're aligning to get the jitter out. Have you explored when you take that aligned data, if you try and find the center of rotation again, does it improve that find, or is it already good enough and you don't have to go back?
Yeah, you should definitely do the center of rotation finding again because you've padded your data. So it won't automatically update the center of rotation when you throw it in, and I should have mentioned that. But so this is now these shifted projections. Again, I'm going to include after a button to just use these as the projections for the rest of the pipeline eventually, and that shouldn't be too terribly difficult. But for right now, after I've shifted these, I need to come back here and look at this new prep folder. So this is the normalized projections again. We'll throw this in. It's going to write down sample data. And now this is what we're going to be using for the reconstruction part of it. So again, you should definitely look at the center of rotation, see how, you know, your alignment affected how well the give me a second. I'll just show you what I mean. It'll come up to center of rotation now. Use this pre-normalized data. It's at 521. We'll again make this search pretty broad, and you can see that the data is more like clean, but these artifacts are from not having the correct center of rotation. So if you come over, okay, so this looks much better. And then we'll just do that one more time. Come to a part that you can kind of see that the artifacts, they're on like either side of the structure. So here, okay, and now we'll just go to a, you know, a lower search range. And I forgot to sort of mention this, but one thing that you can do is you can take your first data set, your raw data set. It's probably going to be super jittery, and so the reconstruction and the alignment might not be perfect. Right, so that's why you're doing this alignment in the first place. But because you're doing the alignment by reconstructing a jittery data set, those reprojected images that you're comparing your raw projections and the other projections to aren't perfect either. So what you can do is after you align with the first alignment, you can go through and just do the same thing again. So you can come to this align tab, run the same sort of process and just fine tune your alignment, which doesn't, again, you know, this was a very short 15 iteration alignment, but it still removed a lot of that jitter. And then you can just go in and you know, run a more fine-tuned alignment on your data. So that's one thing. So you can continue to align it and get you know, get better results for the alignment. Okay, so before, I guess, I mean, we only have like 10 minutes or so. Now you guys can ask any questions. I just want to show you a quick feature for anybody who's doing ZANES. So what we have in this part here is, one second, a tool for shifting projections with high energy projections and low energy projections. So what we can, in ZANES, we can have data sets where we just want to align to the highest energy in that data set, which is typically the most clear data set. So I'm going to load in my align data. So again, I'm going to come here. I'm going to find where I aligned my data. I think it was this folder. Yeah, it should be here. So you can see that's aligned well. And then I want to come to a low energy. I hope I, sorry, I'm going to have to import and normalize it. It'll only take a few seconds. Maybe if you guys have any questions while this loads in, feel free to ask.
So in general, the workflow is to iteratively center the feature that you're trying to look at, right?
Yeah.
So you go through that alignment step several times until it's, I kind of missed the first part of the median filter. Is that something you always have to do, like median filter it, align it, and then take the filter off?
You don't have to necessarily do that. And I didn't have that feature until recently, but I've found that it does improve the quality of the alignment. But if you just, you don't necessarily have to do that. No. I can also like later include just like something where you don't even have to go through that median filter process. You can just click an option to do the alignment on filtered data. Okay, so I just loaded in this low energy import and I normalized it. So then I'm going to come down to this again. Here. Okay, so now I'm going to load this guy in. So this is my lower energy, and we have to do a few things here. We have to correct for the magnification of the lower energy. So we have to shrink this down to fit the magnification here. So click this button, it shrinks the full data set. So now we have a data set that looks identical in terms, well, not identical. This is still really super jittery. And we want to align this jittery data set to our aligned data set. So we can do that. Typically, I can use this full data set without doing anything. So I'll just click this button. Behind the scenes, it's kind of actually doing a median filter to find the shifts of this compared to this. And so now what we have is a somewhat aligned data set. Now, like you can see that there's it screwed up at some point of this alignment, but throughout the full one, it's relatively good. So I want to load this in again. Do this process again. I want to use only a small fraction of it, just like we did previous to this. The reason it screwed up was because of this big blob here, I think, that's coming in and out of the data set. So if I just click and drag on this, it will, okay, so these are changing simultaneously because we have to use an identical region to compare to in either of these images. So you can move this around. You could compare this to this if you wanted to, but you don't want to do that. You just want to compare one part of your data set to a very similar part of your data set here so that it can find the shifts of this data set relative to this data set. So if I now am looking here, maybe I just want to use this part of the data set to compare to. We can link these guys up again. So, I mean, this looks pretty good. I'll just make sure, I don't know, that's probably fine. Now, and I'm gonna do this registration one more time. And it will try to find, hopefully it's done a better job this time of finding the correct positions. It's not perfect, but again, you can just kind of play around with this, and you can also look at this difference map. So you can kind of tell that, you know, this is the images that we were looking at. You can see that this part of this image is not here in the high energy projections, but you can tell that it lines up with the rest of the data. So it's done like a pretty decent job. This is again, this is the low energy, the high energy projections here. You can see this part of the data. It doesn't exist in the low energy projections, but it still matches the feature of the low energy projections. So you can kind of see how this works by just looking at the difference map of these two data sets.